Hi everyone, my name is Shiqi Zhang, a PhD student from NUS. Today, I would like to present you with our effective and efficient way to visualize graphs. This is a joint work with HKBU and SUSTech. Here is the outline for today's presentation. First, I will review the background and related works of graph visualization. Then, I will introduce the proposed visualization solution called PPRVs and the core subroutines in it. Finally, I will share some interesting experiment results and the conclusion. Graph structures are found all around us, which consist of nodes and edges that describe relationships between them. Given a graph with n nodes and m edges, graph visualization aims to generate a position matrix X for G. During the drawing process, the visualization involves laying out each node at its 2D coordinates and linking the two endpoints of each edge with a straight line. The visualization technique is applied in different domains to help users understand the complex relationships in the graph. To make our work easier to follow, I will use examples of undirected graph in the presentation. However, it is important to note that our techniques are also applied to directed graphs. A high-quality graph visualization should have good readability. To evaluate the readability of visualization results, the graph drawing community has proposed several aesthetic criteria. Node distribution and uniform length coefficient variance are two commonly used criteria among them. Node distribution measures the evenness of the distribution of nodes on the screen. A good visualization should have nodes evenly spaced out as shown on the left-hand side. On the other hand, an example of poor node distribution like the right-hand side would have overlapping nodes. For ULCV, it measures the skewness of edge lengths on the screen. An example of poor ULCV like the right-hand side would have distorted edge of variant lengths, making it harder to distinguish between relationships in the graph. Regarding existing visualization solutions, a common way is to show all nodes and edges on the screen, which is called single-level visualization. It generally involves two steps. First, a graph theoretical distance matrix is computed. This matrix can be obtained using either an adjacent related matrix or the shortest distance matrix. Next, the distance matrix is embedded into the position matrix, aiming to minimize the difference between the pairwise distance on the graph and the Euclidean distance on the screen. However, one drawback of this approach is the poor readability of the resulting visualizations, which are often aesthetic unpleasant when the graph is small, or resemble hairballs when the graph is large, making it challenging to interpret the graph structure. Additionally, this method can be computationally expensive, which poses challenges when dealing with large graphs. To address the issues in single-level visualization, many existing solutions adopt the multi-level framework, whose idea is to interactively display the graph in partial view level by level. First, a supergraph hierarchy is constructed from the original graph G. As shown in this example, the bottom level is an input graph G, and we call the node in G as a leaf. We call the upper level a supergraph, and the node inside a supernode. For example, the supernode S in the top level supergraph. In addition, each supernode contains K children in the level below. For example, the children of S are in the shadow area. After a user selects an S to explore, a single-level solution is applied to realize the children of it. Compared with realizing the entire graph at once, presenting the graph in a hierarchical manner can help to avoid the hairball effect and reduce the embedding overhead. However, the aesthetic issue still remains because the multi-level solution also leverages the single-level layout method. To mitigate the issues raised by existing solutions, we propose a graph visualization solution called PPRVs. It adopts the multi-level framework and contains the following three main steps. The first step is the construction of a supergraph hierarchy. It is generated using the famous community detection algorithm LOVIN, while trying to ensure that the number of children of each supernode is balanced. Next, PPRVs introduces a new distance measure called PDist for computing graph theoretical distance. This measure, specifically designed for realization, captures the relationships between nodes in a more accurate manner. To compute the PDist for the children, we then propose an efficient estimation algorithm called tau push. After PDists are computed, PPRVs proceed to perform position embedding, which calculates the position matrix based on the PDist matrix. Its goal is to ensure that the Euclidean distance between pairs of nodes on the screen resemble their corresponding PDist. Here is a visualization instance generated by PPRVs. Here, the circle size is proportional to the number of children inside a supernode. As we can see, PPRVs can clearly show the partial view of each level. Before PDist, I will first introduce personalized PageRank for mirroring the connectivity between two nodes in a graph, which is the core of PDist. Given a source node Vs, a target node Vt, and a stopping probability alpha, PPR from Vs to Vt measures the probability that the random walk with restart from Vs stops at the target node Vt. Take this graph as an example. The node pair V6 and V9 are more connected to each other than node pair V0 and V8. Accordingly, PPR from V6 to V9 is larger than that from V0 to V8. In other words, a large PPR value reflects that the node pair are well connected on the graph and should be close on the graph when realized on the screen. In PDist, we leverage the concept of degree normalized PPR. The dPPR between any nodes Vi and Vj is defined as a product of the personalized PageRank and the degree of the source node. This degree normalization ensures a better realization quality. To convert the dPPR to PDist, we use a formula of y minus logarithm. This transformation helps us represent the dPPR values in a distance-like format, enabling the subsequent position embedding step. Using dPPR as a distance matrix offers several advantages. First, it preserves the high-order information captured by RWR, allowing us to determine node coordinates based on a more accurate graph theoretical distance. For example, to measure the graph distance from V3 to V1, RWR considers the paths as follows. In contrast, the shortest distance only considers the first one. Second, PDist guarantees the quality of realization in terms of ND and ULCV. These two advantages mean that the resulting realizations reflect the topology information while providing a clear representation. Now, I will introduce the main steps of the proposed tau push algorithm. Tau push first computes the tau value for each node, Vj, which is the average of dPPR value from all nodes to Vj. Then, tau push computes a critical constant tau, which helps to trade off the computational overhead of the next two steps. After that, a deterministic version of RWR is invoked from each children Vi to estimate PDist for other small tau children. At last, a reverse graph traversal is conducted from the large tau children Vj to estimate PDist for all other children. Furthermore, the first step and the third step are pre-computed and stored at the index. To evaluate the performance of our proposed PPRVs, we conduct experiments on 12 real-world graphs from different fields, in which the largest graph Twitter contains 3 billion edges. We compare PPRVs with the following realization solutions from different categories. It is worth noting that most competitors have been applied in software and libraries like GIFI, GraphViz, and NetworkX. To evaluate the effectiveness of PPRVs, we compare PPRVs and 11 single-level competitors on 6 small datasets in terms of aesthetic criteria. As reported in the table, we can find that PPRVs can outperform all competitors in terms of ULCV. Here, we also show the realization results of PPRVs and the best competitor FR. In these two figures, we can find that PPRVs shows clearer relationships on film trust and has less node overlapping compared with FR. To evaluate the efficiency of PPRVs, we first report the pre-processing time of PPRVs and multi-level competitors. As shown in the figure, we can find that the pre-processing time of PPRVs is within 20 minutes, even on the largest graph Twitter. In contrast, all competitors fail to return within 12 hours. We next report the response time of PPRVs and all competitors. We skip the single-level competitors that fail to return in 1,000 seconds. As shown in this figure, we can find that PPRVs outperforms all competitors in terms of response time. It only uses several seconds to return the partial view for the largest Twitter graph. To summarize, in this work, we propose a new graph realization solution called PPRVs, which contains a PPR-based distance measure and an efficient PDist approximation algorithm. Thanks for your listening.